share my screen. Okay, so here's what we want to do. I want to sort of motivate what I want to have happen today. So I just talk for a little bit first before we do some math. So let's think about what we did before with our halting problem lecture, which people are really working hard to get their heads around, and I'm trying to help you with that. So everything we did about the halting problem and countability was a rock solid, rigorous proof. And even the TAs who are very sophisticated mathematicians have gone over this with me, and they would agree with this. But the theorems themselves raised a number of questions. And by raised questions, I don't mean that they can't be answered or anything's wrong. I mean that the questions, legitimate questions came up, such as really, what is a function? What's the difference between a function and a procedure? How does this generalize? How can I use it on something else? And we can begin to answer these, but the real answer to these involves the deeper structure of numbers, functions, and sets. And we can give you sort of an answer now. We've tried to do that, but we really need to know more about set theory first in order to answer these questions in a rigorous fashion. So what I will tell you is this. What we have done so far is we have explored sets and functions in this class in a sort of apprentice fashion. So you had some idea about sets and functions based on your intuition and your experience, and the basic operations were mostly pretty intuitive. And you could accept and check complex proofs that I did, and you could do some more simple proofs yourself that we assigned you and asked you to do. And this is super important because sets and functions and relations are the basis for all of mathematics and all of CS. And even in this sort of apprentice fashion, we achieved quite a bit of depth in 13 lectures. We have the substitution model to prove programs are correct. And let me say that without the substitution model, you have no hope of understanding why our proof about safe and safify is correct, because you don't have a semantics. And all the questions that might be asked in person or in Piazza about what does this mean or why is this, the ultimate answer is substitution model. It's hard to give with the intuition sometimes, but we can always grind through the model and see what it produces. Combining substitution and induction, we can prove programs are correct. We prove the square root of 2 is irrational. We even talked about countability and uncountability, different sizes of infinity, halting problem, and streams, which of course I introduced so you'd get a little more comfortable with these infinite series. And even in this sort of apprentice mode, nothing wrong with being an apprentice. When I was an apprentice, I was a grad student at MIT or a staff member at Harvard, and it was the best time of my life. I enjoyed learning things from people who could mentor me. But even in this apprentice fashion, we found lots of counterintuitive results. Infinite series, pretty weird. Infinite sets and streams, quite strange. Countability and uncountability and the halting problem. These are the getting past the foothills of mathematics and starting to look at the large mountains to climb. So in the halting problem lecture I gave you last time, we proved there are undecidable problems, by which I mean unprogrammable functions, making a distinction between functions and procedures, basically. So we use the term function and you have some intuition about that. But now you know that mathematical functions are distinct from procedures. Namely, the mathematical functions are things that make sense in mathematics, but not all of them have a corresponding procedure to compute them. And in fact, not all functions are programmable. This is mind-blowing when you think about it, because we'd like to think that by being systematic, we can program everything, but in fact, we can't. So one of the goals of mathematical computer science is to systematically classify the decidable versus undecidable problems in terms of their difficulty. And sort of like biologists classifying animals. This one can do this one eats the following thing, this one dominates on the Sahara, so forth. So right now that is in this class, we can maybe prove some individual problems are decidable or not. So see essay 10, essay 11, problem set 4, and so forth. But we'd like to have a more systematic way of doing this, if you will, a recipe or some rules or something. And to get there, we need some lessons in the mathematics of sets and functions, so we can really use them in a professional, not an apprentice way. And by the way, this material on sets, functions, and relations is the basis actually for all discrete mathematics and much of the continuous mathematics as well. And I regularly had students previous in this class say, thank you, that cleared up all the stuff I was learning in linear algebra, which is very well taught in my department at Duke, but it clears up lots of other things as well. So the math you'll learn now, it will enable us to explore in a few lectures the concept of what's called Turing reducibility after Alan Turing, which is a deep and really powerful way of classifying the hardness of problems in computer science. And it makes a direct use of the more sophisticated view of sets and functions we now are going to undertake and to study. And let me tell you that as a computer scientist, these lessons in set theory are going to be useful for the rest of your life in every class or job. You'll use them every day. And I'm going to start off quite slow so we have a foundation, but never fear, we'll accelerate. I don't think people are really worried about that. If you find it too easy, then relax. But we will accelerate within a lecture or two to something that is, you know, a bit more challenging. But I want everyone to have this foundation, and this will also help you with your proofs. Okay. So that's it. I want to turn on the document camera now. All right, please let me know if you can see the document camera and if you can hear and see me.
Yeah.
Yes.
Yeah.
Thank you, I appreciate it. Great. All right.
We actually have a question, Bruce.
Sure.
Would it be fair to say that the undecidable problems are those where we have declarative but not imperative knowledge?
In a formal sense, yes. But in a applied sense, no, because they're usually interleaved. So for example, my definition of safe, which was defined, again, declaratively, that's perfectly reasonable. There's quite a bit of imperative knowledge in there because you have to kind of know what procedures are and what they do. So they're a little bit enmeshed. I would say that a clarification of that or a gloss on that very interesting comment would be, it's a situation where you have declarative knowledge, that is, you can define a function declaratively, but there's no way to go from the declarative to the imperative in that case. And maybe we can go more into that. So that's an interesting observation, but it's not quite as simple as that, but very good start. Let's discuss it more if you would like to. Great question. And of course, we'll do a lot more in this area. All right, so let's just talk about sets a little bit, try to get somewhere. Talk about some notation. So I'm going to give you a great handout at some point by Paul Halmas called How to Write Mathematics. But I'm going to summarize the way that we could think about math. So if I have sets, I'm going to denote them with capital letters like A and B. And lowercase letters like A and B, these are elements of sets. And if A belongs to a set A, we write that by A in set A like this. And if it does not, I write that by A is not in set big A like that. So little a, element of set, big set like this. Now, one question is, when do we know sets are equal? Equality. So if we say A equals B, this means that A and B are actually the same object, literally symbols for the same object. Whereas the expression A equals B means that the sets A and B contain exactly the same objects. Now, if A is a subset of B, we write a subset of B like this, as you've probably seen. And that means that all elements that are in A are also in B. Now, we can specify a set in several different ways. And one way that you may have seen is to write a set like this by enumerating its elements, A, B, C, like this. This is a set that contains 3 elements, A, B, C. Or more commonly, what we'll do is we'll take a set A of objects of some property that, and we'll pick, what we want to do is want to say that they satisfy some property. So more commonly, we'll take a set A of objects and specify some property that the elements of the set A may or may not possess. And that will let us form the set of all elements, say, of A that have this property. And this is easier done than said, like many things in mathematics. We'll write the set B is equal to, say, all integers in the natural numbers such that X is even. And of course, you can think about this And of course, we have ways of doing this imperatively, so to speak, in scheme. This is the same as filter stream, even integers. Or more formally, that's what's returned by this. So this is how we'll think of this. So again, this concept of filtering a set by some property is nicely implemented using filter or string filter in scheme, depending on whether your stream is finite or infinite. Now, as you may know, given two sets A and B, you can define their union, and we can use our notation for that. So A union B is defined as all points or elements X, such that X is in A and X is in B. Similarly, this is called union, and we also have intersection. And I know you've seen some of these and even had midterms on them, but I want to make sure we're on the same page before I build on this. So intersection is when you have the set of points that's in both, and we'll write that in set theory as an element X, such that X is in A and X is in B. Oh, or, sorry. I mean an or here, sorry, and an and here. Sorry about that. The union is it's in A or B, and the intersection is it's in A and B. Okay. Now, it's possible that these have no elements in common, and this is called disjoint. So if A intersect B is equal to the empty set, we say the sets are disjoint. Okay. So you've seen some of these things before. At this point, it will be very useful to go over the meaning of if-then statements. Now, they have some intuitive meaning, but there are some complications, not complications, but there's some things to be careful of when you want to, say, do a proof by contradiction and invert or negate an if-then statement. And I want to talk about how we'll do that. So let's talk about the meaning of if-then statements. And I mean in mathematics, are obviously similar in scheme. So if we have a statement of the form, if P, then Q, where P and Q are propositions that are either true or false, the meaning of this in mathematics is that if P is true, then Q must also be true. But if P is false, then we don't know anything about Q. It can either be true or false. And this can be defined by a truth table you can think of like this. So the truth table for if P, then Q can be thought of like this. We put P up here, Q over here, we put true, false, and true and false. And the value of the proposition if P, then Q is true, true, false, and true. And this is actually a definition of the meaning of if P, then Q. So slightly counterintuitive sometimes. Let's do an example of this to try to understand what's going on here. So suppose we have a statement like this. If x is greater than 0, then x cubed is not equal to 0. So this will be the statement P, and this here will be the statement Q, like this. And there's names for these. You can sometimes call P the hypothesis, or the antecedent, and you can call Q the conclusion. So logically, we write if P, then Q as P implies Q like this. And this is a common notation in mathematics. And it's equivalent to the statement with words. Now, if you look at this truth table, you'll see that the statement P implies Q is equivalent to the statement logically, not P or Q. So we haven't used this as much. This is just like the not we have in scheme. And of course, this is the or that we have in scheme like this. And again, the proof of this is just to look at the truth table. So the truth table is the definition of the meaning of if-then, and this is a way of expressing it using a conjunction. So it's a little strange in some ways, but it lets you manipulate these statements. And there's lots more on negation and what it means in the lecture notes that I've handed out for today that are already on the web. Now let's use this to do a little bit of go a little bit further and talk about the contrapositive and the converse. So if we're given a statement such as if P then Q, or P implies Q, we can form its contrapositive. The contrapositive statement is defined by, let's just write this out in words here. This is if P, then Q. Its contrapositive is defined by if not Q, then not P. I sort of wish I'd given this lesson to the debaters at the presidential debate last night, because we could have been spared a lot of logical inconsistencies. So if not Q, then not P means if Q is not true, then P is not true. Let's do an example to clarify this and look at what we had before here. So we're going to start where we were before and say if x is greater than 0, then x cubed is not equal to 0. And this is a good statement. The contrapositive of the statement is if x cubed equals 0, then not x greater than 0, which of course is equal to if x cubed equals 0, then x is less than equal to 0. And I think it's fairly easy to see in this case that if the original statement is true, that is this top line statement here, and indeed it is, if x cubed is equal to 0, then, sorry, this statement here, if x is greater than 0, then x cubed is not equal to 0. It's quite clear to see that the contrapositive is always true in this case. Namely, if this statement here is correct, then this statement here is correct. So if x is greater than 0, then x cubed is not equal to 0. You can deduce from that that if x cubed equals 0, then x is less than equal to 0, which is kind of cool. Let's actually think about this and see if we can prove that in general. So here I've only proved this for one statement here, right? I've shown this for one statement. Sorry, while I pick you up, I have to put in a charging cable because I've already used. There we go. Sorry to make you dizzy. So in this particular case, we have one example that suggests this might be a general rule. So when we have a statement, its contrapositive is always follows from it. So let's write that down as a claim instead. So we have claim. And if then statement and its contrapositive are logically equivalent. So there's several ways of thinking about this. One way is to write out truth tables for each of these and see that they're identical. I think a little bit nicer way is by what I'd call algebraic manipulation. Let me just do it for you. Later you'll do some of these by yourself. So let's take an if-then statement. What's an example of one of these? Well, generically, it's just P implies Q. Now, we'll rewrite this, as we showed was possible before, as not P or Q. And this is just true because that's the definition. Now let's write its contrapositive. The contrapositive is not Q implies not P. And we'll write that in conjunctive form as we had before. That's equal to Q or not P. Let me pause and ask you, do you see why the final step? If the answer is no, then tell me and I'll do it for you. Do you all believe this?
No.
You don't believe it. You want to see it?
Yes, please.
Okay, good. Let's see why this is true. Okay. Well, so if I have, so I start with, the top line is fine, right? That's just the definition. Here's the bottom line. So I'm going to take this, I'm going to write that in conjunctive form, and that's going to be not Q or not P. So for the same reason that P implies Q is equivalent to not P or Q, I could just substitute not Q and not P for that. I get not Q is equal to not Q or not P, and that's equal to this. Does that make sense?
Yes.
Good. Thank you for asking. And so therefore we proved our theorem. So a statement and its contrapositive are always logically equivalent, which is pretty cool, right?
Wait, sorry. How'd you put in not Q?
Sorry, can you ask a slightly longer question?
I mean, like, how did you what was the substitution that you made there? Not Q for P, or?
So look at this first. Look at this in a box. Do you agree with that?
I guess not.
You don't agree with that. Okay, so we just proved that. Let's prove it again. Okay. So here's the truth table that defines P implies Q. So this is definitional. So I can't ask you if you agree because it's a definition, but I can ask you if you understand.
Okay, I see.
Okay, so
yeah.
So we good now?
Mm-hmm.
And are we good for the rest of your question, or should I go on?
I'm still not sure about substituting in the not Q, yes.
All right, so you agree with this, right? You agree with this thing in a box. Okay, so I did that because I'm actually trying to prove this about particular statements P and Q, which is what I should be doing. But I can also, having said this, I can treat this as a generic definition where P and Q are any statements at all, right? So now look down here, I have another implication, right? Right, in this bracket. Not Q implies not P, that's the contrapositive, right?
Mm-hmm.
So now I'm just going to apply this rule here, right? So not Q plays the role of P and becomes not P, which is not Q. Not P plays the role of Q and becomes not P. So this is a direct application of the rule there to get this form.
Oh, okay.
And then I just simplify.
Yeah.
Good. Great question. Keep them coming. And by the way, I think that this is a great example of what mathematics should be. It's not a way of certifying something so someone doesn't have to think about it. It's not a way of convincing someone who doesn't want to be convinced. It's a way of having a discussion. I can write a claim down, and if there's a step that you don't understand, you can say, can you prove that? And then I either can or I can't. This symbol here is the mathematical statement for or. So you don't have to use it, but this is and, this is or, and this is not. And by the way, they mean exactly what they mean in scheme. Okay. So great, we have this. Now, having understood something about contrapositives, it's a pretty deep thing, right? We have two very different looking statements that are actually logically equivalent. But for converse, we have a different story, right? Remember, we had converse. So the converse is a different statement, and it can be formed from the statement P implies Q. And I think I want a fresh piece of paper because this is kind of a little bit mind-bending. So this is another way to form a statement out of P implies Q. So given the converse is Q implies P. So be very careful to distinguish the converse from the contrapositive. They're very different. So a statement and its contrapositive are logically equivalent, but the truth or falsity of a statement says absolutely nothing about the truth or falsity of its converse. Let's look at an example again, our same example before. So here's our example. If X is greater than 0, then x cubed is not equal to 0. And this is actually true, which is nice. Now, if we transform that into its converse, which means just write a new statement, we get the statement if x cubed is not equal to 0, then x is greater than 0. So let me ask you, this is the new statement called the converse. Is this statement true or false for x being numbers?
True.
False.
Yeah, I think it's false. Why is it false?
X could be a negative number.
Yeah, that's a good example. So we could have a counterexample. X equals negative 2. So it could be true. I mean, a priori it could be false, but there's no connection between these two things. So again, a statement and its contrapositive, always logically equivalent. Statement and its converse, not equivalent. So the truth or falsity of a statement says nothing whatsoever about the truth or falsity of its converse. You can see an example of that here. But sometimes the statement and its converse are true, which is a happy circumstance. So if we have P implies Q, and we also have Q implies P, because these are independent things, we can write this as a double arrow like this. Sometimes written in English as P holds if and only if Q holds. So a special notation in this case, P if and only if Q, which is great. So sometimes that does happen. All right. So these are very helpful ways of manipulating if-then statements, which are ubiquitous in mathematics, especially when we have to do something like negate them to do a proof by contradiction, like assume the opposite by way of contradiction. Well, what's the opposite? Why would it be true? Why would it not be true? Okay. All right, so very good. Also very good questions from the studio audience. Let's go on a little bit. So I want to define one more way of combining sets. I'm going to do this on this paper, which is called set difference, which you may have seen. And then we'll have a lot of things at our disposal. Set difference. So if we have two sets, we can define the difference of the two of them. So if we have sets A and B, I'll write the set difference as A minus B like this. This is the set of all elements that's in A but not in B. So all elements X, such that X is in A and X is not in B. So now we have three different set operations that we can kind of visualize this way. Now these visualizations are not proofs, but they're ways of thinking about sets that can be useful. I'm sure you've seen some of these before, but let me illustrate them because I will occasionally use these to illustrate a point. In each case, these sets represent A and B. And here we're going to have A union B, A intersect B, and A minus B. And we can illustrate these like this. A union B is everything here. A intersect B is just the things that are in both A and B. And A minus B are the things that are in A that are not in B, which corresponds exactly to this definition here. Now some notation or terminology. A minus B, or the set difference A minus B, is sometimes called the complement of B relative to A. Complement here is spelled with an E because you're completing something. It's not spelled with an I, which is something nice about the set. What a very nice set you are today. You're looking very well. Which is the butt of many mathematical jokes. We will use the term complement with an E only when the context or what we're complementing. The problem is you have to specify both of these things. So I sort of prefer the set difference terminology here, but there's nothing wrong with the other one as long as you're clear. Now, as you've seen for if-then statements and for logic, there are rules for these things, and sometimes the rules give you interesting theorems. There are also rules for set theory. So given several sets, you can apply operations to form new sets. So we can apply the set theoretic operations, namely union, intersection, and set diff. And we can apply them in some fashion to these sets and even nest these operations to make new sets. So we now have several ways of making sets. So as in algebra, we parenthesize these to indicate the order of operations. So for example, we can write something like, let's see, I have a new piece of paper here. So we can write something of the form, let's see, A intersect B, sorry. I want to do it a different way. Sorry, that example is harder. So I'll flip the page over. I could say A union B intersects C. And I can compare this to what? To A union B intersects C. So the first one here, A union B intersects C, this denotes the union of A and the set B intersects C. Whereas the second thing over here, this denotes the intersection of A union B with C. And one interesting thing is that the results of doing these things are actually dramatically, fundamentally different. And we can illustrate that. This is not a proof, but it's an illustration why they're different by, again, drawing our sort of Venn diagrams. Let me try to do that for you. Here I'll have A, B, and C. And here I'll try to draw the same thing again. And with this symbol, our class needs a biosafety level 3 certification because that looks like the biohazard symbol. So let's see what these operations actually are. So A union B intersects C, well, that's the following thing. Let's do B intersects C first. B intersects C is this region in here, like that. And then we take A like this. So everything in red there is A union B intersects C. Whereas over here, when we do them in a different order, we get something really very different here, right? So what we do here is basically we're going to take A union B, which is these things here, and we're just intersect those guys with C. So that's just going to be this region here. So as you can see, these sets are dramatically different things, right? The order of operation matters quite a bit. So it's not the case, if you're thinking of kind of what you learned before, it's not the case that intersection and union do not commute in the sense you might have learned in algebra in high school or maybe even other class. It's actually that they don't associate, which is even a worse problem, so to speak. So to be careful with these operations, you can get some unusual results. But fortunately, sometimes different combinations of operations actually do lead to the same set. And when that happens, one has a rule or theorem in set theory saying the two things are equivalent. So by contrast, I have something like this. So here's two different things. So I'll call it a theorem. It's a fundamental theorem of set theory. For any sets, A, B, and C, we have, I'll call this theorem 1, A intersect B union C is equal to A intersect B union A intersect C. So these are actually equivalent. Let's do an illustration of this, but a picture of this is not the same as a proof. But looking at what this means sort of algebraically, you can kind of think of this law of set theory or theorem as a distributive law for the operations intersecting and section and union. In some sense, on the left-hand side here, we have an intersection that's going to be distributed over the union like this. And this is worth proving, and so we will at least sketch the proof here. So how would we kind of get our heads around this particular problem to try to do this? Now, how do we know this theorem is true? So let me draw some pictures and let me reiterate to you very clearly. I know you can see me because I spotlighted my video. These diagrams are to give you intuition about how to prove things. They are not a proof. We do not accept proofs from other mathematicians, including TAs and professors that are these drawings. The proofs are the kind of going through the details of what happens with the elements that I'll do in a moment. But these drawings can give you intuition for what's happening, and they can illustrate the plan you want to make for your proof. So let's try to get some intuition for why this rule should be true by again drawing our set intersections and getting some concept of this. So I'm going to do this 3 different ways here. And come up with a rigorous proof. Okay, we have A, B, C in each case. All right, so let's just think about some of the basic things here. Over here, what I want to illustrate is just B union C, which will be this area here. Now over here, I want to illustrate A intersect C. See, I've written a tautology here. I mean to write. Yeah. So the reason I'm doing this, I want to look at some of the terms that appear here. So I illustrated B union C because I want to dig into that term. Now I want to look at A intersect C to get an idea of what's going on there. Right? That's why I wanted to do that. So let's just get an idea of what's going on here. Let's do A intersect C. That's going to be everything that's in A and C. So it's going to be this little region like this. And over here, I'm going to have A intersect B. And that's going to be this little region here. So now I've actually understand all these terms. I mean, I assume you know that A is just this disk here. B union C is the union of these 2 disks. A intersect C is the intersection of the disks A and C. And A intersect B is the union of the disks A and B like this. And so we can sort of think about this intuitively by saying, well, why should this be true? Let's look at the left-hand side. That says we're going to take, basically what it says here is that we're going to take B union C and intersect it with A. So we're going to get this region in here that's contained like this. So basically the region that's in here, let me draw that again. So in that case, on the left-hand side, we're going to start out with so we know what A is. We're going to intersect A with all of this here, which is B union C, and we're going to get a set that looks like this. So that's the left-hand side. What about the right-hand side? It's going to be a similar kind of construction. Again, we'll have A, B, and C. This says what we're going to do is we're going to take the union of this region here, which is A intersect C, with the union of this region here, which is A intersect B, and we're going to get the same looking thing. All right, so this is intuition. It's not a proof. It's why these things should be equivalent. But it's useful for us to do this because we can get an idea of what the operations are actually doing and we can visualize them. So I always think it's great to do these drawings, and it sort of tells you what's going on. Now, how would we prove a thing like this formally? And I want to mention that in this class, there have been some questions about formal. We're actually not as interested in formal as we are in rigor. So I would say this is an illustration of a proof. It's not a rigorous proof. Rigorous proofs don't have to use a lot of notation, but they should be completely convincing. So what about a proof? How would we do this? So let's take a look at that. So we'll write out our theorem again. So we have it on the same page. And we'll say A intersect B union C is equal to A intersect B union A intersect C for any sets whatsoever A, B, and C, which is pretty neat. So one of the things we need here is we need sort of a recipe for proving that two sets are the same. And there's several of these, and we're going to talk about them. But one of them that is very useful is the following. So suppose I have two sets D and E, and I want to show they're the same set. So to show a set D is equal to a set E, we need only show that D is a subset of E and E is a subset of D. So, and I'm just going to do this in one direction, and I'll let you do the other, and we might do more of these in recitation. So let's look at our example here. So we want to prove this here. Let's just do this in one direction. One direction. So we'll do A intersect B union C is a subset of A intersect B union A intersect C. Notice I'm just doing one direction corresponding to this. You have to do the other direction. I'll leave that for you to think about. So what I'm going to do here is I'm basically going to go back to my definitions of sets, right? I don't have set difference here, but I have also other things like set union and so forth. So we're going to go back to our definitions of intersections and unions and use these. So for example, remember, union is all elements, all objects such that X is in A or X is in B. Intersection is all elements such as X is in A and X is in B. So I'm just going to use these definitions here to try to unravel what's going on here and then use a little bit of logic. This isn't hard, but there's a little bit of bookkeeping. All right, so show using these following techniques. So the way to show that D is a subset of E, many ways, but one way is to pick an arbitrary point in D and show that it must be in E. And since your choice was arbitrary, that will be true of any choice of points in D. So I'll do that by saying let X be some point in the left-hand side, X intersect B union C. So groovy, we've got that. So then, what do I know? Well, if X is in A intersect B union C, then I know that X is in A or X is in, and X is in A and X is in B or X is in C. So all I've done is I've broken this into language about the points. So again, if X is a point in A intersect B union C, then I know that X must be in A and either X is in B or X is in C. So that's fine. So what can I conclude from this? Well, we can just break this up a little bit. We can say X is in A and X is in B, or X is in A and X is in C, right? Because that's what those things mean. Hence, we can write X is in A intersect B. Why? Because that's the meaning of this statement here. So when X is in A and X is in B, that's the same as saying X is in the intersection of A and B. Or, same thing, X is in A intersect C. Why? Because when X is in A and X is in C, that's the same as saying X is in the intersection of A and C by the definition of intersection. And we finally conclude that X finally is in A intersect B union A intersect C, because that's the meaning of being in either set. And you can show, okay. So that's how we can show that sets are the same, but it's also how we can prove these various laws or theorems about set theory. Okay. Any questions about this kind of proof, which is a little new to us? That's why I want to introduce it, to show that sets are contained in other sets.
What is that last symbol you used? You show.
Oh yeah, that's a great point. So that it's subset going the other way. So let's just review what this means. So A is a subset of, say, D. This means for all A in A is also in D. Okay, now, if A is a subset of D, we can also write it like this. So D contains A as a subset, which is just the other way around. So these are equivalent statements. See what I've done? Just turned it around. So it's just like less than in mathematics, right? If I have 2 is less than 3, I can write 3 is greater than 2, right?
That's why your need only show is like that. It's basically saying for all D in D, D is in E, like for the first part.
Well, these are subset relations. These are not element of relations.
Okay, so then, yeah, do you mind explaining the need only show?
Well, yeah, that's a really great point. Let's try to prove that. Let's try to prove that the recipe is reasonable. So this is kind of a meta proof. So claim. So let D and E be sets. So I claim that D is equal to E if D is contained in E, is subset of E, and E is contained in D, right? So that's really the claim that we have to prove here. So suppose not. Suppose this were not true. So the situation, there could be various ways this was not true. But without loss of generality, suppose there exists a point E in E such that E is not in D. Does that make sense? I just have to look at one case here. So I'm looking at a case like this where I have, that's one way this could not be true. The sets could not be equal. So there could be a number of ways for the sets not to be equal. They could be not equal because they look like this. They could be not equal because they look like this. They could be not equal because they look like this. And they could be not equal because they look like this, right? So those are all the ways that the sets could not be equal. Let me ask, do you agree with what I just said?
Yes, I do. And just to clarify, the C looking symbol, like at the top where it says need only show D, and then the symbol E. So that's saying D contains in E?
It's a subset relation.
Subset, okay.
All right. Would you like me to continue?
Yes, thanks.
All right. So I'm going to prove one of these and leave the other 3 to you. So which one of these, 1, 2, 3, and 4, would you like me to prove?
Let's do the first one.
First one. Okay. So
Sorry, I just need some clarification. Suppose for some E and E is.
let's cross that out. We're going to let him choose which one we're going to prove.
Oh, okay, got it.
Yeah, yeah. I was going to choose for him, but I decided to make it more interactive. Although I'm going to rewrite that. All right, so this is the situation that could, I'm not saying it could happen, but suppose the sets aren't equal and suppose they're not equal this particular way. So you'd have to do a case analysis, right? You have to show it in these fashions. But so what could happen is you could have a situation like this where you actually had points there. So without loss of generality, I'm going to assume, I remember that, I suppose not by way of contradiction. So by way of contradiction, I'm assuming that there's a point here called E. And E is not in D. So, and it's going to be symmetric. I could also do it on this side too. So I could say, suppose that there exists some point E in E, but E is not in D. Let me ask you, are you comfortable with what I'm doing?
Yes.
Okay, good. So if that happens, then we have that E subset D is false, which is a contradiction. Do you buy it? What do you think? And we assume that, right?
Yep. Yeah, thank you.
Yeah. So to complete the proof, I mean, probably there are direct, maybe more direct ways of doing this, but to complete the proof, you'd have to do the other case where you had a D in here. You'd have to do the disjoint case, the two entirely contained cases, or at least one by symmetry. But it would be a very similar argument. Yeah, so this is a kind of a recipe or meta proof technique for doing this. Okay, given that we've proved that this is sound, with a few little lemmas for you to do, any questions about the manipulations I did here to show that this theorem is true for sets? Any questions? Ask now. I'm happy to go through it, or ask anything. Do you believe this proof?
We have a question of what is the backwards E?
Backwards E. I don't see a backwards E. Oh, yes, that's a good question. So in mathematics, this can be a symbol for there exists. And this is a symbol for all. Usually used as there exists an X such that X squared equals 2. Or for all Y less than 0, some statement about Y. Good question.
Would you mind
Sorry,
pushing the paper up just a little bit so we can see what you've written at the bottom?
Oh, I'm sorry. Thank you. Yeah.
That's great.
Yeah. We've used these in class before, but we're going to use them more heavily now. So I'm very glad to have that question and clarify it.
When we would be going through like one of the other examples, like the D with the E inside the circle, inside the set, would it be the same? What would the supposed statement look like in that case?
Yeah, we can do another one like that. Let's do it. Let's see. I think I can just do it down here like this. So which one did you want to do? 3 or 4?
Either.
All right, sounds good. All right. Well, let's do 4, and then the proof is exactly the same. All the text here is exactly the same. So now what I do, I'm imagining E looks like this. And the reason is we only did one of there are 2 symmetric cases you have to do here. You have to consider an E and you have to consider a D. But in this case, it's particularly easy. So we say, suppose the sets aren't equal. Suppose there exists some little point E in the set E, big E, but it's not contained in D. Well, then the statement E is a subset of D is false, and we get a contradiction because we assumed it. Does that help?
Yes, thank you.
Sure. No, good question. So we've done more, which is good. All right. All right. Any questions about this before I move on to another Pretty cool thing. All right.
Yeah, for the above proof, do you mind explaining? I followed up until the hence statement.
Up until the hence statement. So let me see. So you buy this here?
Yes.
Okay. Yeah, let's definitely go into that and talk about it a little bit. Great question. All right, so I'm just going to kind of write it down here like this again. So given, my camera frozen? No, just for a second. Given we have the statement X is in A and X is in B, or X is in A and X is in C. That's the statement, right? And I want to conclude what we have right below this. So when I go from the so to after the hence. So this is a characterization of an intersection. So let's just do it with a generic variable. So the intersection of two sets, say F intersect G is equal to all points X such that X is in F and X is in G. This is the definition of intersection. Are you good with me on that?
Yeah.
Okay, good. So now I just want to instantiate this. So if I have a thing that looks like the right-hand side, I can write the left-hand side. And so I look at this thing here. X is the same. I let F be G. Sorry, I let A be F and B be G. Apply this definition, and I can immediately write this as A intersect B. And similarly over here, I can immediately write this as A intersect C, right? And I can run OR between them as before, just applying the definition of intersection. Does that help?
Yeah, and then can you go one more step down where you
Sure.
do
From the hence to this here?
Yeah.
So going down one more. Okay, that's fine too. Let's do the definition of a union. So F union G, this goes back to, I mean, we wrote this definition a few pages back, but it's good to write it again. So the union of two sets F and G is defined as all points X such that X is in F or X is in G. So these only differ by what the conjunction is. Is it and or is it or? So now if you look at what I have here, and I'm going to write it again for clarity, just rewriting this. This is, X in A intersect B or X in A intersect C, right? That's what I have for right before. So let me ask you, two questions. Are you good with this definition of union? And do you agree with this statement here, which we just derived?
Yes.
Good. So now I just applied the definition again. The definition of union takes this parameter, so to speak, the sets F and G. So in calling it, so to speak, here, I let F be A and G be B, and I apply this definition. I have the OR like this, and then I come down here to X is now a point in A intersect B, union A intersect C. And I'm done. What do you think? Does that help?
Yeah, thank you.
And do you buy the proof now? Yes.
Yes.
Good. Okay, good. Yes. Always okay to ask someone that to understand the proof. All right, more questions on this before I go on. Okay. All right, let's do another cool thing. So what we've seen here is that union, intersection, set difference, these are ways of forming new sets from old sets, which is pretty cool. But there's another way to form new sets from old sets. We've seen a little of this. And it involves the notion of ordered pair, which is very much like the scheme notion of ordered pair. So when you studied geometry, one of the first things you probably did was to try to convince yourself that after one has chosen an x-axis and a y-axis in the plane say that every point can be made to correspond to unique ordered pairs, say x, y, of the real numbers. And so we can think back to geometry or even calculus, and we have our x-axis here and our y-axis here. And if we have a point in the plane, this corresponds to the point x comma y, where the first coordinate is x and the second coordinate is y, like this. And that's our notion of the plane in some sense. And in a more sophisticated treatment of geometry, the plane is actually defined as a set of all ordered pairs of real numbers like this. And of course, this is very nicely implemented in the scheme in two different ways, either as actual pairs of things of type pair, or as lists of length 2, which let you deal with these things very nicely. So the notion of ordered pairs carries over to general sets, not just the real numbers. So given two sets A and B, we can define their Cartesian product. This is named after the great philosopher and mathematician Descartes. Now, I like to capitalize these things because I like to remember the human origins of mathematics, but some people make it lowercase instead. So the Cartesian product, roughly speaking, given two sets A and B, is defined to be the set of all ordered pairs A comma B, of which when A is in A and B is in B. So formally, the Cartesian product of two sets A and B is defined as A cross B. Yes, that's a multiplication-like symbol, but it means something different here. To be the following thing: the set of all ordered pairs A comma B. You could think of that as the ordered pairs in calculus, pairs in scheme, lists of length 2. They're all the same, such that A is in A and B is in B. Extremely useful. Here's some examples will be helpful. So what is the set defined like this by R cross R? Who knows what this is? What do you think it looks like? Any ideas?
The set of all A, B such that A, B are in R.
That's correct. And do you have a name? Have you encountered that before? Have you seen a name for this?
No.
Yeah. So this would be our plane over here. This, yeah. So a few people have done this. Would be the plane would be like this, the Cartesian plane. But if we add a little structure to this, this is actually the set of all complex numbers. And we have to define operations on this, like plus, minus, divided by, and times. But we can define that underlying set is the set of all pairs of real numbers, which is just our Cartesian plane like this. So good job, everyone. How about this one? Z cross Z, where Z, of course, is the integers. What's this? What does it look like? Any ideas?
It's like all the points in the XY plane that are both integers.
Yeah, integers. Exactly. They're all points in the XY plane or the Cartesian plane that have integer values, not rationals, integer values. So it would look sort of like this. Of course, it goes on infinitely. You know, this would be 0 if you will, but that would be like 1, 2, 3. Now this set actually has an interesting structure too. Remember, these were the complex numbers. These actually have a name. These are called the Gaussian integers. They have the form, if you look at a point like this, and you think of this point as being A comma B, you could also think of that as A plus BI. And of course, these guys are a subset of the plane. So the complex numbers are very interesting. They're closed under addition, subtraction, multiplication, and division. The Gaussian integers are only closed under multiplication, addition, and subtraction. So they're what's called a ring, not a field. Very interesting objects that arise. And of course, there's a correspondence that we see here that I've already mentioned between the Cartesian plane and the complex numbers. So if we look at R cross R and the complex of numbers, we could take a pair here, A comma B, and that corresponds in the complex numbers to A plus BI. So we could also look at subsets. So that was kind of cool to visualize. Let's look at some others of these. What does R cross Z look like? What's this set look like? Any ideas?
Would it be the Cartesian plane, but just the integers for the y-axis? Does it hold to the axis? Like, does the fact that it comes first or the second term, does that matter in computing the product?
The order matters a huge amount, but in some sense. So we had an answer that I actually saw in the chat, miracle of miracles, mirabile dictu, which was it's lines at all the integer values. So this looks like this. So look at this. We have a copy of the real numbers like this, right? And that's at 0. Then we have another one at 1, another one at 2, another one at 3, another one at 4, like this, right? So these are y values here. And the x values are unconstrained. They can be anything. That's the x coordinate. The y coordinates are quantized. So we have them at 0, 1, 2, 3, 4. And of course, it is a subset of R cross R. So lines at every integer value was the good answer. All right, given that, and related to this question, what would Z cross R look like? Any ideas? Vertical lines instead. So Z cross R looks like this. Of course, he's going on forever, right? Because look at what I have here. This means that it can be written as sets of XY pairs, right? Such that X is in the integers and Y is a real number, right? Now, one thing about this is that we can define a correspondence. We can go between these, right? We can just flip A and B and B and A. So we could take a point here, A comma B, and we could flip it to B and A. So in some sense, these things can match up. In other senses, the order matters quite a bit. Let's do another one. Getting back to discrete math a little bit. What does the set R cross the discrete set 1, 2, 3 look like? What do I get here? Okay, we can write this out as so what does this set look like if I illustrate it?
Would it be just 3 horizontal lines on y is 1, 2, 3?
Yeah, exactly. So let's draw it out. So here's our plane here, and I'll take 1, 2, 3. This is y values. And then this set will look like that. So 3 copies of the real line going out to infinity like that. Okay. So good. We're getting some intuition for what these sets look like. We can make all sorts of marvelous stuff.
Real quick, mind if I ask a question?
Sure.
Back to the Z cross Z. So we got the Gaussian integers if we kind of took the ordered pairs as like coordinates in the complex plane, but could we also take z cross z, like those ordered pairs, to mean, you know, a numerator and denominator, and so that would be kind of the same as the rational numbers?
So you can define a surjective map from the z cross z onto the rational numbers, but it's not the same, mostly because 1/2 and 2/4 map to the same thing. So they're very
Okay.
similar, and also you have some zero denominators. So remember, mathematicians are very big on representation, and so I can say that you have a really good intuition there, and kudos, great job. But being the same is a very high bar. So not equivalent, but closely related. But yes, I can construct all the rationals from that for sure by dividing it. Great question.
Thanks.
Sure, terrific. Let's do one more. Let's see. Well, so we can define sets in other ways. I can say, define the set S1 to be the circle. This is the set of all pairs x comma y in the plane R2. R2 is my shorthand for R cross R, such that x squared plus y squared equals 1. So I'll ask you what this is, but I think you can pretty much see that S2 is going to be exactly, very good, circle. And here's one for you all to think about. What if I asked, what is S1 cross S1? What does that look like? Okay, so I'm going to leave you to think about this one. We'll do a little more, maybe recitation on that, some of these Cartesian products, and you can think about these. But let's talk about what we did. We actually did quite a bit today. Summary, set theory and logic, some notation. We did intersection union. We did if-then statements, contrapositive versus converse, set difference. We did these laws of sets. These are often called the distributive laws or De Morgan's laws. You may have seen them if you took an engineering class because they apply to circuits. And finally, we did Cartesian products. And these will be the foundation by which we're going to be thinking about sets in the rest of the class. So of course, these all have an implementation in Scheme. As you've seen, sets can be implemented as lists or streams. Ordered pairs are implemented as either pairs of lists or lists of element 2. We can use filter to define sets. And of course, union, intersection, and set difference you can implement, and you've even been asked to do some of that even on midterms and problem sets. So there's a close relation between the mathematics and the computer science here. In other words, computer science is the constructive extension of mathematics that lets you build these things by themselves. Mathematics is the declarative knowledge that tells you theorems about how these things hold. That's going to conclude our lecture for today. I am going to, at this point, hop off myself and leave the Zoom here running, although I'll turn off the recording because I would like to, I have a thing I have to do. I have to go see a guy, I got a thing, and I am going to let you know that the TAs are going to stay on for a while, and they're going to answer your questions. And I'm being slow here, so I'm trying